Hi, I'm Alessio Spagnoletti, and I'm going to present my work to ICCV 2025. The title of my work is LATINO-PRO, Latent Consistency Inverse Solver with Prompt Optimization. So let's see what we are working on. The main task that we're going to solve is the task of inverse problems. This means that we have an observed measure y, and we want to restore like an x given that we know an operator a that created this measurement. We also consider a setting which we add Gaussian noise as it's common, and we can see like an example, for example, with in painting. A main important tool that we're going to use that is good to know about is the latent diffusion model. So latent diffusion model basically instantiate a diffusion model in a latent space of a variational autoencoder VAE. This means that we have an encoder, we have a decoder, and in the latent space, we can see that we can model, like from a Gaussian distribution, we can model a complex distribution that once decoded will target, for example, some type of images. There are a lot of works that have been using diffusion models and latent diffusion models to solve inverse problems. Here I listed some of them probably more famous ones. We can see that a lot of them are based, for example, on the idea like the one of DPS to take gradients in a latent space. And this is important because these are big drawbacks of this type of algorithms. For example, the first one is that diffusion models usually what they do is that they discretize like an integration of an SDE or an ODE. This means that we need a lot of small steps to efficiently sample from the target distribution. And usually we can even need like 1000 neural function evaluations. The other drawback is that in methods like DPS and similar, we need to differentiate through the network. And if we are in a latent space, this means that we need to differentiate through both the decoder and the score network, and sometimes even the encoder as the PSLD algorithms requires. These two things makes this method very heavy and slow, and we want to solve these problems. So to do this, we want to introduce like a new framework that has been like developing in the last years. That is the one of consistency models and obviously latent consistency models. The idea of a consistency model is to, let's say, define and then actually train a network that implements a function called consistency function. What is a consistency function? If we consider the typical SDE of a diffusion model, and we have the forward and the backward SDE, we can actually take the backward SDE and we can find an equivalent formulation that is called the probability flow ODE, which is an equivalent ODE. It has the same marginal distributions, but is not stochastic, while it is deterministic. This means that once we sample from the noise, all the rest of the ODE path is obviously like determined. And this means that if we are at the beginning and we want to get a final sample from the data distribution, we can actually just learn an integrator. We can learn a map that maps directly each noise point toward a data point in a sort of, let's say, generator, like with the GANs, for example, style. Obviously, we can train this network, this generator, to work at different levels of noise, meaning that if we are in the integration from the noise to the data, we can stop at whatever point in the middle and we can try to learn a map that from this point jumps directly towards the final or almost final point x0 at time 0. We can also, once we have this map, we can like formulate an algorithm that iteratively tries to jump to the end, adds against noise, and then go back again to a clean sample. We can do this, for example, 3, 4, 8 times. And the point is that since this network will not be perfectly trained, it makes sense to ask for more than one single step. But usually with 2 or maximum 4 steps, these models can generate images that are at the same level of quality of latent diffusion models. So we are ready now to finally introduce what actually we are presenting, which is the algorithm called Latino. The idea of Latino is the one of using these latent consistency models to solve inverse problems. And in particular, since these models require usually just a few number of iterations, this model will be automatically fast. We require a few neural function evaluations. In particular, we stick to 8. And the second point is that for the way in which we design the algorithm, we don't need to take gradients, and we actually rely on a different type of data fidelity term. And then this model is prompt conditioned, which means that we can actually also integrate a prompt that will condition, obviously, the generation of the sample. And for all these reasons, our model is faster, lighter, and allows like high resolution generation of images with prompt conditioning. And then we also introduced the LATINO-PRO, which actually really exploits this prompt, optimizing it as a parameter that will obviously improve the quality of the restored images. The mathematical formulation of the Latino actually starts from the Langevin diffusion. So we know the Langevin diffusion can actually sample from, for example, in this case, the posterior distribution, P of x given y and a prompt c, and we can use Bayes' rule to split it into parts, and we have the likelihood that we know how to compute, and then we have the prior that is conditioned on c. The main problem is that this integration is really hard to make in a fast way, which is also so efficient and precise. And usually, like the discretization error can be a big problem. This is why we actually introduce this way of like integrate the SDE, which is a split integration approximation. So we split in two parts, one that tackles only the prior, so the first equation, and the second one which only tackles like the likelihood part. And the second part, the likelihood part, is actually like an implicit Euler step, which is something that is stable even for large deltas and is easy to compute because it's actually linked to the proximal operator that can be computed in closed form for a lot of like linear, for example, operators. And then we have the first part, which is actually the one that takes care, let's say, of the prior. And this one is obviously it's not possible to integrate it exactly. But what we can do is that we can approximate the first equation using what we call the stochastic autoencoder as SAE. A stochastic autoencoder is something derived from a consistency model and is actually what we see in the first part of this picture. So we have like a encoding part where we actually have the real encoder of the latent model, so the VAE encoder. Then we have the forward, the P of zt given z0, which is the forward step of the diffusion model in the latent space. And then we have the decoder part, which takes this noisy latent code and actually denoise it in the latent space using the consistency model, the latent consistency model, and then we actually apply the decoder of the VAE. This is something that looks like an autoencoder, and we call it stochastic autoencoder because it actually operates not on single samples, yet it can operate on single samples, but it actually is interesting what it does to distributions because we can actually study the flow of a distribution when it gets in and when it gets out. So indeed, like the main point is that how do we build this stochastic autoencoder? We have, like, as I said, the part that concerns the forward SDE. Then we have the decoder, the encoder, and the consistency model. Some properties that future work will study for sure about like the mathematical soundness of this, but what we can already say is that if x comes from the prior distribution, when we encode and decode using the stochastic autoencoder, we still get something that is distributed in the same way. This means that this distribution, not the sample, but the whole distribution, the prior one, is a fixed point of this like contraction, let's say, function. For different distributions, obviously what happens is that this like stochastic autoencoder actually progressively contracts samples toward the prior. So if we get a different distribution in input, we will slowly converge toward the prior. And this is something that we actually want. And this is the main property of the stochastic autoencoder. And this is the same property that the integral that we integrated before in the first step has. So both have the same properties. We can approximate one with the other. We can again see what I was just mentioning of if we have, for example, like in the left case, a sample coming from the same distribution of the prior, let's say P of x given a prompt that says it's a dog, we see that even when the time t is really big, that means that we are giving a lot of power to the prior because in the encoder part of the stochastic autoencoder we're adding a lot of noise. actually we find as output something very close to the input. While in the right case, when the prior is a cat and not a dog, we can see that, well, as soon as the time t keeps increasing, we leverage a lot on the prior. So we are shifting the distribution input, which is the distribution of images of dogs, towards the distribution of images of cats. When t is small, in both cases, we get basically the identity map because the stochastic autoencoder tends to the identity when the time t is really small. Now we are ready to introduce the LATINO-PRO version. So we are based on the same setting, but we add an optimization step on the prompt. So the prompt can be obviously optimized by marginal likelihood, as is written here. And the motivation is that in a lot of problems, like sometimes the likelihood is weakly informative. So we want maybe to try to get more information from what we can see, and we want the prompt to help us in retrieving this information. So the main thing is that we can actually write a stochastic approximation proximal gradient (SAPG) scheme that helps us in doing gradient ascent basically on the prompt. And the main point is to compute this score here, this gradient, and we can do this through Fisher's identity that allows us to approximate, to compute first exactly and then to approximate, as we can see here below, our score using some samples generated by the same Latino algorithm. So what we do is that we take this expectation and instead of computing different, like in a Monte Carlo way, different samples with Latino, we leverage the intermediate samples. This actual formulation, even though it's an approximation, is very useful because in practice leads us to a closed form that we can actually leverage in the algorithm without adding more like a computational load to our algorithm. The main point is then actually to do these things multiple times until we are, let's say, happy with a specific prompt. We can see now some like results, some tables, and we can see the LATINO-PRO and Latino both improved by a lot, like the metrics like FID or PSNR on different examples like Gaussian blur and super resolution times 16, which is really high. In this case, we're working on the AFHQ dataset, which, for instance, is made of this type of images. So we have dogs, we have cats, and we can see like these two examples that tell us like how Latino and LATINO-PRO are able to retrieve very well some information of some like fine textures, for example, and some details without hallucinating too much. In particular, LATINO-PRO helps a lot in avoiding too much like hallucination, as we can see in the fur of the dog, for example. We have a similar table for the FFHQ dataset, so faces dataset. Also here we are comparable, if not better, to state of the art in a lot of different metrics, and in particular we can see on the number of function, the neural function evaluations that is much lower than all the other methods. And here we have also some examples that really are interesting to understand how the prompts conditions the final outcome. We can see like in this case where the blur is very heavy that we can condition on different prompts and we can get different outputs, all of them compatible with the observation. While when we also want to optimize the prompt, so in the LATINO-PRO case, we can actually see how the metrics like the LPIPS or the PSNR actually aligns when we optimize. So these graphs below show that if we start, for example, from a wrong prompt that is like, I don't know, a photo of a cat when actually we want to restore a dog photo, like the one above, we can see that at the beginning we have a larger LPIPS and a lower PSNR, but when we iterate the Latino optimizing the prompt, what we do is that we are actually improving the metrics, and as we can see from the above images, what the prior will sample at the beginning, that is like a cat, actually with the optimized prompt, the prior will sample something that is closer to a dog and also recognize some features like the color, for example, of the fur. And this helps a lot in the restoration that is obviously improved as we can see from the metrics. These are other examples when we can see that the prior sample, so generated without any conditioning, using just the prompt, a photo of a dog, is the one on the left, while if we optimize, we can learn some features from the corrupted measurement that will help obviously in the restoration of the whole image. And finally, we can also see how our methods both are very light in terms of GPU and are also very fast. if we compare with similar methods at the same resolution, which is 1024 squared, we are much lighter and faster than all the other state-of-the-art methods. For future perspectives, obviously, as I mentioned before, we can also try to give some theoretical properties, like some theoretical motivation and analysis in particular of both Latino and LATINO-PRO. In particular, for example, for the Langevin split stepping, we can try to understand why this works, and we can test on different types of distributions where we know how to compute in a closed form all the different steps. And then we can also try to develop strategies to automatically adjust the parameters. For example, the delta that we saw, which plays a big role actually in the integration scheme. And then we can try to decode the optimized prompt and see actually what the model has learned. And obviously, we can apply this to blind inverse problems. Thank you very much for your attention, and I hope to see you in ICCV.